Reacting masses and volumes. 1. Perform calculations including use of the mole concept, involving F. Reacting masses, from formulae and equations, including percentage yield calculations. We use the relative molecular mass or formula mass in grams, 1000 g equals 1 kilogram. The number of moles of a substance can be calculated by using the mass of the substance and the relative atomic mass, AR, or relative molecular mass, Mr. Finding the mass of a substance present in the provided number of moles requires simply rearranging the equation. There might be a probable need to know what mass of each provided reactant is required for the reaction so that they react exactly and there is no possibility of waste. To figure this out, we need to know the chemical equation of the reaction. This exhibits the ratio of moles of the reactants and products in the reaction. The balanced equation shows this stoichiometry. For example, in the reaction, 1 mole of iron, 3, oxide reacts with 3 moles of carbon monoxide to form 2 moles of iron and 3 moles of carbon dioxide. The stoichiometry of the equation above is 1, 3, 2, 3. The numbers that are present in the above equation, 3, 2 and 3, are called stoichiometric numbers. For us to find the mass of products produced in the chemical reaction, we use the mass of the reactants, the molar mass of the reactants, the balanced equation, the stoichiometry of a reaction if we are aware of the amounts of each reactant that will exactly react together and the amounts of each product formed. For an illustration, if we react 4.0 g of hydrogen present with 32.0 g of oxygen, we get 36.0 g of water in the reaction. AR values will be H equals 1.0, O equals 16.0. This ratio is the ratio of stoichiometric numbers in the equation. We can still calculate the stoichiometry of this reaction that is taking place even if we do not know the mass of oxygen that is present and reacts. The ratio observed of hydrogen to water is 1:1. However, there is only one atom of oxygen in a molecule of water, half the amount in a present oxygen molecule. So the observed mole ratio of oxygen to water in the equation must be 1:2. B. Volumes of gases, e.g. in the burning of hydrocarbons, equal, same, volumes of all the gases present contain the same number of molecules. This idea is approximately accurate as long as we understand the conditions of pressure, which should not be too high or the temperature too low. Hence, it is convenient to measure volumes of gases at room temperature, 20 degrees Celsius, and pressure, 1 atmosphere. At room temperature and pressure, RTP, 1 mole of any gas has a volume of 24.0 dm3. Hence, 24.0 dm3 of carbon dioxide and 24.0 dm3 of hydrogen both constitute 1 mole of gas molecules. Also, we can use the molar gas volume of 24.0 dm3 at RTP to find volume of a given mass or number of moles of gas present. Mass or number of moles of a given volume of gas present. Note, if we mix 20 cm3 of hydrogen with 10 cubic centimeters of oxygen and explode the mixture, we will find that the gases have exactly reacted together and no hydrogen or oxygen remains. If equal volumes of gases contain equal numbers of molecules and hence equal numbers of moles of gases. Hence, the mole ratio present of hydrogen to oxygen is 2:1. We can extend this idea to experiments involving combustion data of hydrocarbons. The example provided below illustrates how the formula of propane and the stoichiometry of the equation can be calculated. Propane is a hydrocarbon, a compound of carbon and hydrogen only. Alternatively, the formula for finding the volume of gas can be used, which is gas volume, dm3, equals amount x24. Note, this equation gives the volume of a gas at room pressure, 1 atm, and room temperature, 25 C. C. Volumes and concentrations of solutions. The concentration of a solution is the amount of solute dissolved in a solvent to make 1 dm3, 1 cubic decimeter, of solution. The solvent is usually water. There are 1000 cubic centimeters in a cubic decimeter. When 1 mole of a compound is dissolved to make 1 dm3 of solution, the concentration is 1 mole 3. We use the terms concentrated and dilute to refer to the relative amount of solute in the solution. A solution with a low concentration of solute is a dilute solution. If there is a high concentration of solute, the solution is concentrated. When performing calculations involving concentrations in mole 3, remember: change mass in grams to moles. Change Cm3 to Dm3 by dividing the number of Cm3 by 1000. There is an occasional need to calculate the mass of a substance present in a solution of known concentration and volume. To do this, we rearranging the concentration equation. We know 2. Number of moles equals concentration, mole Dm3 times vol Dm3. Multiply the moles of the solute present by its molar mass. Mass of solute, G, equals number of moles times molar mass, mole 1. Note, titration. Titration is known as a technique where a solution of known concentration is used to determine the concentration of an unknown solution in the reaction. Calculations of titration require the above knowledge, examples of which are seen through titration. A titration is known as a technique where a solution present of a known concentration is used to determine the concentration of an unknown solution in the reaction mixture. We can use titration results to find the stoichiometry of a reaction. To do this, we need to know the concentrations and the volumes of both the reactants that are present. The example below shows how we can deduce the stoichiometry of the reaction that takes place between a metal hydroxide and an acid that is present in the reaction. D. Limiting reagent and excess reagent. Here, we do not always require the molar mass of each of the reactants present. If one or more of the reactants is present in excess, we need only know the present mass in grams and the molar mass of the reactant that is not in excess, the limiting reactant. Example: deduce the maximum mass of titanium that is produced when it reacts with 100 G of TCl4 with 80 G of sodium. E. Deduce stoichiometric relationships from calculations such as those in 2.4.1, a, d. The balancing, stoichiometric, numbers are mole ratios, e.g. 1 mole of N2 reacts with 3 moles of H2 to form 2 moles of NH3 as products. Typically, the quantity of one substance is given and you are asked to calculate a quantity for another substance in the reaction. Any of the provided equations above 3 can be used. Step 1. One of the above 3 equations can be used to convert any given quantity into moles. Mass moles. PVT of gas moles. Concentration and volume of solution moles. Step 2. We must use a balanced equation to convert moles of initial substance into moles of the second substance. Step 3. Convert the moles required for second substance into quantity question required by using relevant equation, e.g. moles, Mr. Mass. Mole, P, T gas volume gas. Moles, volume solution concentration. Note, when performing calculations, candidates' answers should reflect the number of significant figures given or asked for in the question. When rounding a number off, candidates should make sure that significant figures are neither lost unnecessarily nor used beyond what is acceptable. When we solve chemical calculations, it is very crucial so that we answer the number of significant figures that fits with the data provided. The examples exhibit the number 526.84 rounded up to varying numbers of significant figures. Numbers rounded to 4 significant figures amount to 526.8, these rounded to 3 significant figures amount to 527, then rounded to 2 significant figures would amount to 530. When you are writing an answer to a calculation, the answer should be to the same number of significant figures as the least number of significant figures in the data.